Hi, my name is Mahesh Balakrishnan, and I'm here today to talk to you about Delos, which is a system that we've built over the last 3 years at Facebook. The key idea in Delos is virtual consensus. And in the first half of this talk, I'm going to describe how we used virtual consensus to enable online upgrades of running services. And this is work we presented last year at the OSDI conference. But in the second part of this talk, I'm going to describe how we used a similar idea to scale Delos in the number of engineers working on the project. And this is a new idea that we're describing for the first time in this talk. The Facebook software stack consists of two different layers. On the top, you have a data plane, which is storing and processing large amounts of data. And at the bottom, you have a control plane, which consists of infrastructural services like naming, sharding, configuration, and schedulers. An example of a control plane service is Twine, which is the Facebook scheduler, which we also presented at OSDI last year. Now, in 2017, when I joined Facebook as a new software engineer, the control plane needed a place to store its state. And there were two properties required for this store. First, it had to be exceptionally fault tolerant because it was at the bottom of the Facebook stack. So if this store goes down, the site goes down. And second, it needed a rich API. We needed transactions, secondary indices, range queries, and so on. As the control plane was getting more sophisticated and capable, it needed all of these features. Now, the problem was that Facebook had a number of existing storage systems at the time, but none of them satisfied both of these imperatives. So, for example, some systems like Zookeeper provided exceptional fault tolerance, but did not provide a rich enough API. And at the other end of the spectrum, systems based on SQL offered a very expressive API, but did not match the fault tolerance of Zookeeper. Now, at Facebook, we have a number of very good engineers. So, one natural question is why can't you just take an existing system and add whatever is missing to it? The problem is that the design of such systems tends to be very monolithic. So, it doesn't lend itself to easy evolution. So, for example, a system like Zookeeper has two parts. There's a database up on top and a consensus protocol at the bottom. And it's very hard to change one of them without changing the entire system. So when I showed up in at 2017 at Facebook, the problem statement really was the control plane needed a new storage system that had both a rich expressive API, but was also exceptionally fault tolerant. And the problem was that we didn't have years to build such a system. We had to do it in months because the control plane needed that functionality right away. So in some sense, magic was expected. Now, I used to be a professor before I came to Facebook. And when I taught, distributed systems, I would tell my students half jokingly that in systems, we only really have a small number of good ideas. One of those ideas is abstraction, where you take a complex system and you break it up into constituent pieces, each of which has a very cleanly defined boundary. And the second such idea is virtualization, where you take each of these abstractions and you virtualize it so that you can have any implementation behind and you can switch between these implementations easily. And what I'd say in class, again, as a joke, is if you have these two techniques, you can do magic. So here I was at Facebook, and I was faced with this nearly impossible task of building a new storage system with extreme fault tolerance guarantees really, really quickly. And these were the techniques I had at my disposal. So what did I end up doing? Now going to talk about what I call the great Delos magic trick. Now, if you Google magic trick, or if you remember watching the Christopher Nolan movie from a few years ago, you know that a magic trick has three stages. In the first stage, which is called the pledge, I show you something very ordinary. For example, maybe I show you a rabbit. In the second stage, which is called the turn, I do something surprising. For example, I make the rabbit disappear. And in the third stage, which is called the prestige, I do something even more surprising. I make the rabbit reappear. Well, the Delos magic trick is something like that, except instead of rabbit, we have zookeeper. So in step one of the trick, I show you something somewhat ordinary. And What that is we take Zookeeper and we layer a table API on top of it. So here's what we did. We built a new single node storage system that has a table API, and we ran three copies of it for fault tolerance. So this is in the diagram, you can see this is the thing that says Delos table. And then we kept these copies synchronized via the abstraction of a shared log. So there is that magic word abstraction. And further, we virtualized the shared log abstraction so that under the hood, we could map the shared log to any underlying implementation. And in version 1 of the system, we built such an implementation simply as a shim over Zookeeper. So again, what did we do here? We took Zookeeper, slapped the shared log API on top of it, and then we materialized a different table API on top of that. So this is the first part of the magic trick, the mundane part, where I just show you something that's fairly ordinary. We have Zookeeper, we make it look like a log, and we run a database on top. And it turned out that many teams at Facebook have actually used this exact technique to get very similar results, using Zookeeper as a log. But here's now the surprising part of the magic trick, where we make Zookeeper disappear. And the way we do that is we took an additional few months to implement a consensus protocol on our own, a custom built native consensus protocol. And then we leverage the fact that the log is virtualized to very easily switch it from using the Zookeeper based log to this new custom log. Now, when we did so, Zookeeper vanished because it was no longer in the stack. So, what we had effectively done in something like a year and a half is build a brand new storage system with a table API that did not have a dependency on Zookeeper. But here is the really surprising part about this trick. Having made Zookeeper disappear, we then made it reappear as not at the bottom of the stack as a log, but at the top of the stack as an application. So we reused a lot of the logic that we had in Delos table to create a Zookeeper clone called Zealous. So now we had two systems running on the same platform, and we didn't need to maintain a separate Zookeeper code base. Now, to explain this a little bit more, here is what the architecture looked like. I call it an hourglass architecture, where at the top you have applications like Delos table, for example. In the middle, you have this common piece of platform code. It includes the virtual log and it includes functionality above the log for things like efficient playback, backup, and so on. And at the bottom, you have log implementations. And as I told you, we had two implementations of the log where you had a Zookeeper based one and a native one, and we were able to switch between those. And up on top, we can have multiple applications. So we have Delos table, we have Zealous, and so on. So the reason this looks like an hourglass is you have a very wide top where you have a lot of diversity in the applications you can implement on this platform. You have a very wide bottom of the stack where you can have many log implementations and you can switch between them on the fly. But at the center of the stack, you have this common platform layer that's reused across many applications and many logs. So this was at this point a fairly successful project. We had been running it for 2 years in production without any major issues. We had roughly 2 billion transactions per second every day, which is a very decent number for the control plane. We wrote up a paper about the architecture, submitted it to OSDI. It got accepted, got a best paper award. So at this point, we could have just declared victory and gone home, except it turns out that things are not as smooth. The problem with an hourglass architecture is that the hourglass has a bottleneck in the middle of the stack. So when we started building Zealous out, we had deployed Delos table and now we wanted to deploy Zealous, the second application. The team that was driving this was the existing Zookeeper team at Facebook. So they were reusing the code that the Delos team had built. And we found that the Delos platform became a bottleneck for them. So I don't mean a bottleneck in terms of throughput or number of nodes or the usual systems metric. I mean a bottleneck in terms of development, in terms of how many engineers could work at the same time on the project. So very specifically, Zealous was blocked by the platform in multiple ways. First, Zealous needed guarantees that Delos table did not provide. So Zookeeper has this session ordering property that's stronger than linearizability within a session. And we needed to provide that Delos table does not need this property, and hence the Delos platform did not provide it. Second, to replace Zookeeper at Facebook, Zealous has to achieve performance parity with Zookeeper. And for this, they need a number of optimizations like batching and group commit. These have to be done in the platform layer. So again, they were blocked waiting for the platform to have these features. And finally, Zookeeper has advanced features like observer mode that again could not be layered above the platform. They needed the platform to incorporate such features. So instead of unblocking innovation across teams, the vision was that the Zookeeper team could build Zealous, the Delos table team could build Delos table, and the platform would support both. Instead of unlocking all of this innovation, we ended up blocking multiple teams. So we had very unhappy engineers because they could not get their job done. Now, I said, before that in systems, we only really have like two or three really good ideas. And I already mentioned abstraction and virtualization as two of them. Um, and, there's a paper by Butler Lamson, the Turing Award winner, written in the 80s, where he gives a lot of useful advice to system designers. And one of those pieces of advice is use a good idea again, maybe because we don't have that many of them in systems. And so that got me thinking, how do I use these two really powerful ideas, abstraction and virtualization, to get me past this new set of challenges? So here is what we ended up doing, and this is the new idea in this talk. We came up with the idea of a log structured protocol, and I'm going to describe to you what that is. So if you look at the Delos architecture, the way I described it, you have these apps up on top, like Delos Table and Zealous, which are thin layers of code. And then below that, you have this big common platform code, right? And below that is the log. Now, the problem with the platform was that it was really this big hunk of monolithic code, and you can't have multiple teams changing it very easily. So what we did is take that big hunk of code and split it up into smaller pieces. In some sense, if you think of the Delos platform as a replicated state machine, we took that state machine and virtualized it into smaller pieces. And by doing this, we're able to decompose functionality in a modular way so that multiple teams can work on individual pieces separately. But that's not all. A log structured protocol is a state machine, but it's also a protocol. So, for example, we can layer these protocols between the log and the application almost the same way that you layered network protocols in a network stack. When the application appends an update to the log, it passes through each layer, and each layer can add its own header to the entry. And when we play an update, each layer processes the entry, extracts its header, and can do something useful with it. So, why are log structure protocols so important? How did they help us? Well, the first thing that a log structured protocol lets you do is you can deploy new applications very quickly because you know that you can evolve them later. So, for example, an application like Delos Table can be rolled into production with just a couple of protocols in the stack. One for basic replication, for playing back the log and so on, and one for tracking the number of durable copies of the database so that you can trim the log. Now, down the road, when the customer needs more features from you, it's very easy to now change the database to provide those features. For example, with Delos Table, we had customers come to us and say, can you give us point in time restore? And for that, we needed to store a backup of the log in some safe location so we could go and play it back. So the way we did this is just by implementing one more protocol, a log backup protocol, and we inserted it into the stack and got this new feature. So adding new features to deployed applications is very easy with this approach. But really, where things get interesting is that we can now support multiple applications easily on the same platform. So, for example, to roll out Zealous, we were able to take most of the Delos table stack, everything except the app on top, and we just substituted the app with Zealous. The benefit of this is you can take an existing battle hardened stack of code and redeploy it for a different purpose. Now, as I told you, the Zealous team, when they did this, they were blocked by the lack of additional guarantees in the Delos stable stack. So the way we got around that is the Zealous team implemented a new protocol called the session ordered protocol, and they inserted that into their stack. So this was a way for Zealous to customize the stack for its own use case without in any way disturbing the reliability or the performance of the Delos stable stack in production. So two teams are now able to share the same code while still customizing it in various ways. And one of the things that Zealous ran into is that they needed to get performance parity with Zookeeper, which means they had to optimize the middle of the stack. And the way they did that is they went off and they wrote a new batching protocol on their own. Now, this is really surprising to me because so far we did get a lot of code reuse between Delos Table and Zealous, but most of it was one way. Delos Table had already built components that Zealous could use. This was the first time that the Zealous team built something on its own that was immediately reusable across both their own application as well as Delos Table. And tomorrow, if someone builds a third application, this component will just slot in right there and accelerate performance. So this was a real vindication of the vision of a reusable platform that you can use across applications. And finally, one of the blockers for Zealous was that they needed advanced functionality like observers. So in Zookeeper, you can have a node that's just observing the update stream as it goes past without actually mutating it. And the way we achieved that in Zealous is we simply ran two versions of the same stack, except that one of them was running a stripped down version with some of the protocol layers missing. And this is really powerful too because you're running the same code, you're just running a subset of it in a different location. This means it's very easy to keep these two stacks synchronized with each other. If you change a protocol and you deploy it in one stack, you're going to get it immediately in the other one. Now, to conclude, we really had these two big ideas, abstraction and virtualization. And a lot of the Delos project was about taking replicated databases and figuring out what the right abstractions are and how they should be virtualized. And in the process, we get all of these benefits like online upgrades and what I call happy engineers. Now, for an engineer in the Delos ecosystem, there is just a lot of opportunity in terms of how to innovate. So, for example, you can build a new app on top of Delos. If maybe you want to build a queuing service, maybe you want to build a SQL database, it's very easy to just build one more application on top. Or you could go and build a new log structured protocol. For example, maybe you have some really clever optimization to accelerate state machine replication. It's really easy for you to build that as this composable layer and then deploy it across these multiple applications. And finally, if you want to muck around with the consensus protocol at the bottom, if you have a new idea for how to do Paxos more efficiently, we have a way for you to implement that protocol and we can switch our deployed production systems without downtime to a new protocol. So at the end of the day, we are unblocking innovation. We have a lot of bright engineers at Facebook, and maybe the primary goal of this project was to allow all of the really good ideas to see the light of the day as quickly and efficiently as possible. And in the end, deploying code is what makes engineers happy. So that's what we got with Delos. We got happy engineers. Thank you very much.